Okay. Hello guys. So I'm Marcel. Our project is SM behind the meter residential solar power. Our problem statement is that there's just a huge gap in the market on PV system like capacity and output, and we're potentially trying to like fill that market, especially with like from the company perspective, electric supply allocation, overall grid stability management. Our aim to develop a machine learning model is to give a certain geographic location to detect solar panel arrays within an area that around that location and estimate the yearly solar power generation of those panels. Our objectives and requirements, we have design objectives that will be from there, and then we also have system requirements to fulfill those design objectives. All right, so our system design, so we grab their addresses and then Google Solar API will be able to give us the necessary information to be put into the YOLO V8 segmentation. And our post-processing will give us the necessary information for the address monthly flux. And then we will be able to put this into an equation to calculate for our predictions. All right, let's go ahead and move on to our web demo.
Hello, my name is Riley, and I'll be going over the data collection of our project. So the goal for this part is to obtain satellite and aerial imagery for anywhere in the United States, so we can make estimations for any client need. For input formats, we'll allow for three. We allow a list of addresses, a list of latitude, longitude coordinates, or you can specify a center point, specify the height and width, and we can generate a grid of images to cover a wide area, such as like a city if you wanted the solar output of that city. Here's an example of a grid like that stitched together. So for all of our imagery, we get it from Google Solar API. For visual imagery, it's always square. We can specify the resolution and we can specify how much area it covers in terms of meters, so how big kind of what we want the picture to be. But what we cannot specify is the quality of the image or the date of the image. Some images are older than others, and some images, especially in more rural areas, are grainier and not as good of a quality as some. So we'll have to account for that in the detection and the estimation portions of this project. In addition to that, we also get data maps from Google Solar API, which is very useful. So here on the right side, you can see what's called a solar flux map. And what this does is it shows effectively how much sunlight each part in that image is getting. So this is very useful when we have detections of solar panels because you can overlay this map with how much sun that solar panel would be getting in order to get an estimate for how much power at a maximum that panel could generate within a year. We also incorporate the building mask from Google Solar API, and that's essentially just a map on the image that will tell you where a building is and where a building isn't so that you can pinpoint certain addresses and determine the solar output for those addresses. All right, moving on to annotation and detection.
Hi, my name is Victoria. I'll talk about annotation a little bit. So we using the images that we collected, we wanted to scale off of that to account for like the budget limit that we had. So we took the 1,000 images that we collected and we cropped it into 4 quadrants and ended up with 4,000 640 by 640 images. We used RoboFlow to manually annotate our data set, which was the test data set and the custom data set. And we ended up employing the segment anything model to convert the square bounding boxes into polygon bounding boxes to improve our model detection. And the model that we ended up choosing was YOLO V8. It's YOLO V8L for the square bounding boxes and YOLO V8 seg for polygon detection and segmentation. Yeah, and then these are the images, example images from RoboFlow on the data sets that we used. And I'll hand it over to Seal to talk about detection more.
Hello, this is Seal, and here on the left, we have a chart demonstrating how different fractions of the training data we use to train our model affect the performance for the detection on the validation task. We use from 50% of the training data up to 90%. And here we use 4 metrics to demonstrate our performance. While for precision, varying the fraction, the amount of training data doesn't affect the performance that much. But for MAP, which is mean average precision 50 to 95, by this metric, we can clearly see that increasing the training data set clearly brings improvement in performance for the detection. And then down, please. Here for the 2 data set, namely the bounding box, square bounding box data set, we use the YOLO V8 model, and for the polygon data set, we use the YOLO V8 segmentation model. While for both data set and both models, the prediction on square bounding box at mean average precision 50 are comparable. The YOLO V8 seg model can predict the mask for the solar panel area, and we can use post-processing to calculate the solar panel area, and then combined with the solar flux map and also the building mask, we can estimate either the monthly or the annual energy production by the solar panel.
Hey, my name is AJ Solano, and I'll be going over the PV estimation. So once the panels were detected from our model and the flux data was gathered from the Google API, we were able to formulate our findings into a CSV file. This data, we can calculate the monthly potential, where array area is generated from our detection model. Peak power size is taken. We keep our system losses at a constant 14% for each region of interest. This is because if we wanted to incorporate weather data, then we would have to either plus or minus that percentage. And then the monthly data radiation is taken from the flux map layers generated from Google Solar. Good to keep in mind that we do not account for weather. And we also optimize our panel tilt. That is from the Google API. They take that into account when they're calculating their flux. We also don't account for major weather events such as solar eclipses or snowstorms. And we also do not account for soiling or degradation as the years goes by and the module efficiency decreases for each solar panel. At first, our scope was only within Washington State. We had a pool of 5 solar panels, and we took into account factors such as GHI, GDP, and types of environment in order to estimate which solar panel would be used in each region. And we used their respective data sheets to get the system performance percentage to use as the value of our module efficiency. If a county isn't in Washington, but is requested, then a default of 22.8% is used. And it's also good to note that we weren't able to gather that much ground truth to verify our accuracy and our estimates. This is due to data being private to customers or unobtainable from utility companies like Seattle City Light or Puget Sound Energy. However, we did compare our results to other solar panel power estimators such as PVGIS or PVWatt. With this, we saw that our results varied for each address. This may be due to the weather data we didn't account for. And it's also good to keep in mind that we ran our estimate for the houses that not all the houses detected on the image, only the ones that's centered. However, if we wanted to broaden our scope, we could do it for all the houses in the image. Once the data is collected and our estimates are made, we're able to output all of our findings onto a CSV file as shown below in the final output.
Cool. So I'm gonna introduce you guys to the fun part of our demo. My name is Larry, and as you can see, for our demo part, we have a collection of addresses that we collected beforehand and pre-processed offline. So if we click on one of these example addresses, we'll find the address, and we have images to show the pipeline of our project. On the left, we have the RGB image that you could find on Google Maps. Transitioning further, we have the detection model image. So this is the image after we use our detection model. So you can see that there's bounding boxes for all of the solar panels that you can see in the image. And then on the right is the solar flux map, like Riley mentioned. And at the top, we have information that's important to our estimation. So panel area and annual flux that we collected. And with this data, we generated a PV estimation in kilowatt hours. And at the bottom, we have a graph for the monthly potential of this house. And so you can see it's pretty accurate. As you see, we have the summer months being higher potential than the winter months, which is on track as there's more sun during the summer. And yeah, and you can click on any of our addresses and we'll have information like this for all of our addresses.